So the first paper will be presented by Dibyasree Guha, Debashish Bera and Bhaskar Bishwas, and the title of the paper is Security Analysis of LDPC Code-Based Encryption. So I invite the presenter to present the paper. Thank you.
Thank you, sir. Am I audible?
Your voice is very low.
Is it okay now?
Yes, a bit better. Please share your screen.
Yes. Okay, a very good afternoon to everyone. Opening with a brief introduction, my name is Dibyasree Guha, and I'm presently researching on the topic of cryptanalysis of LDPC code-based crypto system under the guidance of Dr. Debashish Bera of the Indian Institute of Information Technology, Kolkata. So he is also the co-author of this paper titled Security Analysis of LDPC Code-Based Encryption, along with my fellow colleague, Mr. Saurabh Bishas. Without much further ado, I would like to resonate what Shrikant Sailadas said, that the need for post-quantum cryptography, also which is known as quantum-resistant encryption, is basically driven by the increasing belief that quantum computers with which have power to break the current public key infrastructure cryptography will be available within a span of maybe 5 to 10 years. So in lieu of that, NIST started a competition to select standard post-quantum encryption algorithms back in 2016. Now, NIST's call for proposals identified three basic aspects of evaluation criteria. So the aspects are basically security, cost and performance, and thirdly, algorithm and implementation characteristics. So based on that, we are basically focusing our research on a quasi-cyclic low-density parity check code-based public key encryption scheme, which is known as LDPC, and LDPC had made its way to the second round of the competition by NIST. So before going to LDPC, I would first like to give a brief background on code-based cryptography. So in the search for good alternatives to classical crypto systems, where
I think you have to speak a bit louder. Not able to hear.
Okay, sir, just give me 1 second. Maybe there is some problem with the mic. Sir, is it better now?
Yes, yes, now it's definitely better. Okay, go ahead.
Okay. So, as I was telling, with number theory as the backbone, the good alternatives to classical crypto systems, code-based systems has emerged as a strong competitor for post-quantum cryptography. Now, the reason behind that is that decoding a random linear code is a non-deterministic polynomial time problem, and that would not depend upon the computation power of the adversary. Now, public key crypto systems are mainly aimed at ensuring secure data transmission over an insecure channel. And forward error correcting codes, basically what is the basis for code-based system, they are concerned with minimizing errors when sending data over a noisy channel. Now, data sent from one point to another not only needs to be untampered from malicious interventions, but they must also not undergo changes that might be attributed to the drawbacks of the medium, the communication medium. So it was back in 1978 when McAleese proposed a public key crypto system based on coding theory, wherein he found the interrelation between public key crypto systems and forward error correcting codes. The main idea of McAleese was to send more information or redundant information through the channel than what is actually needed. Now, if this redundancy has a structure, then it would be exploited in order to correct possible errors that might occur in the data transmitted. Now, code-based cryptography uses this very concept. The original Macaulay system used GOPTA codes as the component encoder, which has a very big drawback, which is that it results in large key sizes, and hence it is difficult to actually implement for real-life applications. This actually forms the basis of our study on quasi-cyclic low-density parity check code-based encryption, which is the LDPC. Now, LDPC has Macaulay as well as need-editor crypto system as its basis, as its basic building block. Now, the main advantage of using QC LDPC codes instead of GOPTA codes is that these codes have sparse and circulant nature for the parity check matrices, which allows a considerable reduction in the key sizes. And in turn, this actually renders to efficient decoding techniques. So hence, I proceed to discuss in brief the Macaulay crypto system. So it basically comprises three algorithms, that is the key generation, the encryption, and the decryption. Though for the key generation, the receiver first chooses an arbitrary GOPTA polynomial, say gx, with a degree t over the field fn2. So this is a field of order 2, and it has got n elements. Now, using this, the receiver will compute something which is the generator matrix. It is a k cross n generator matrix of the GOPTA code. And further, two other matrices, S and P, one is an invertible matrix and the other is a permutation matrix, will be chosen by the receiver. Armed with these three matrices, he computes G dash, and the public key would be the G dash. So G dash is SGP, and T is also part of the public key. The private key consists of polynomial GX, the original Macaulay, the original matrix G, that is the generator matrix, along with the S and P matrices. So the sender can encode his or her message. So it is a k-bit message M by computing mg dash plus E. So M is the message, multiply it with the public key, and the error, E is basically the random error vector which has been added for transmission. The decryption part, the receiver will use his permutation matrix to compute Y dash. So Y dash is the Y, the message that actually was sent, P inverse. So it is basically mg dash P inverse plus P inverse applied also on the error vector. So likewise, we get msg plus EP inverse. Now, EP inverse is the actual error that has been added, since P is the permutation matrix. So from this, the message M can easily be recovered. Now, any adversary or an attacker has two basic attacks to try. One is to recover G from the public key G dash so as to be able to use Patterson's algorithm. So the problem with this is that this is difficult because if the sufficiently large sizes of n and t, so if n and the number of errors and the actual parameter n is quite large, it is there are a lot of possibilities of the values of S, G, and P. So for Macaulay, there was around 10 to the power 149 types of GOPTA polynomials that could be possible. So that is not possible. So this attack is rendered not possible. Apart from this, another attack could be to recover the message M from Y without learning G. Now, this is also a difficult problem because this would involve decoding an NK arbitrary linear code in the presence of T errors, which is, as I said, this is an NP complete problem. So this renders the attack infeasible as well. So next we proceed to describe the QC LDPC code-based Macaulay. So LDPC basically, it involves a quasi-cyclic code C of the order Pn0, Pk0, where the Cnk is basically a binary code which maps a binary sequence from 2 to the power k field to 2 to the power n field. The generator matrix and the parity check matrix of the quasi-cyclic code is basically a collection of n-naught number of P cross P block circulant matrices, where block circulant matrices are matrices wherein every row or column can be obtained by circularly shifting the very first row and first column respectively. So just the knowledge of one row or one column will enable us to generate the entire matrix. And the information length for QC LDPC is K0, which is P times N0 minus 1. Now, the parity check matrix of LEDA crypt allows for efficient decoding techniques, which are called bit flipping decoding. This is allowed for the sparse, this is applicable for the sparse nature of the QC LDPC code. Now, the BF decoding, the bit flipping decoding algorithms, it relies on the notion of flipping the bits in the error affected code word as long as either an all zero syndrome is obtained, which indicates the all zero syndrome indicates the removal of all errors from the code word bits. Or it would stop and if it reaches a predetermined number of iterations, say I max. The public key of QC LDPC code-based MAC list looks somewhat like this, where Z is a P N0 cross P N0 identity matrix, which is composed as a diagonal block matrix, wherein we have N0 minus 1 replicas of the identity matrix I for I from 0, and M is constructed by L N0 minus 1 inverse into Li. Now this L is nothing but the private key, basically, of QC LDPC based MAC list, which is actually computed by combining a block circulant matrix H and a quasi-cyclic matrix Q. Okay, so this would give us the private key, and the public key would be a combination of the inverse of the last block of the private key along with the other blocks of the private key. Now, next we proceed for the security analysis. Now, different types of cryptanalysis are possible on this type of QC LDPC code-based system. My main focus is on information set decoding, and information set decoding dates back to 1962, where it was invented by Eugene Branch, and later on it was improved upon by a lot of scientists, and I'm mainly focusing on the improvements by Lee and Bricken and Stern in the year 1988, and finally it was revisited recently, if I may say so, in 2015 by May and Ozerov. Now, before going into information set decoding, what I have done is how this can be applied for the attack on QC LDPC based MAC crypto system that I have discussed. So basically, a key recovery attack is possible by exploiting information set decoding. So given the public key of MAC crypto system based on QC LDPC code, a passive attacker may wish to perform a key recovery attack. So he considers two distinct integers, I0 and I1, and a matrix P is defined as follows. The matrix is P cross N0 P. So A is basically a matrix where there are N0 number of P cross P circulant blocks. And it has got a certain pattern, a speciality, that is every block of A is 0 except two blocks, Li1 and Li0. So Li1, AI is Li1 if I equal to I0, and AI is Li0 if I equal to I1. From this particular form of the matrix, it is found that if we multiply this with our secret matrix L that we were talking about, so AL transpose would actually give us a 0. So what we have found is that A is the null space of our private matrix, this private secret parity check matrix. So this actually goes to show that the rows of A are code words of C. So for a matrix to be a parity check matrix of a code word, the code must be the null space of that matrix. So this is driven by the logic that if H is the matrix and C is the code, and C are the code words of the particular code, then H into C transpose would give us a null. So this actually goes to conclude that the rows of A are code words of C. Now, as each block of Li is a circulant matrix, as it has to be since it is the multiplication between H and Q, Thus, C must have a minimum distance of 2B. Now, if an attacker is able to determine one of the rows of A, then he will be able to recover two blocks, Li and
Conclude.
Lj of the secret matrix L.
Hello? Yeah, please conclude.
Yes, sir?
Please conclude faster.
Okay, sir. So this is the basic key recovery attack that would be exploited by ISD. So ISD basically we are using ISD to find low weight code words. So for that we actually perform certain calculations or computations over the given parity check matrix. So instead of using the parity check matrix H, what we do is we permute it and we pre-multiply it with a matrix U. So that gives us H dash. So H is transformed to H dash, and the similar permutation is allowed on C, the code word. So C gives us C dash. So P is chosen, that is, a permutation is chosen in such a way that the first R columns of the transform parity check matrix are made independent. So H basically becomes H dash, which is of the form X followed by the identity matrix of dimensions R cross R. So this very form is exploited by the different ISD techniques. So the technique by branch, what it does is that it assumes that the permutation that we are applying on the code word, that permutation takes all the weight, the entire weight W of the code word in the last R positions, and the first key positions are kept as 0. This has been little improved by Librickel, where Librickel allowed P number of ones to occur in the first K positions, leaving W minus P ones in the last R positions. Stern further improved the timing on this by dividing the first K positions into two halves, that is K by 2 and K by 2, and P1s are allowed to occur in the first K by 2 positions, P in the next K by 2 positions, and the last positions will be W minus 2P. Mayozerov actually does the same thing as Stern, but instead of just you randomly looking for the set of P1s, it actually involves nearest neighboring technique in order to make the search faster. So here I have a table where the different ways in which the code word is broken up has been discussed, and the stopping condition. So basically this is a representation of the algorithm of the different ISD techniques. So after this, we proceed to perform our results and analysis. So on the basis of the data available with us and the parameters that are provided by the LDPC authors, it has been found that as expected, Librickel has a lower cost, and Librickel has a higher cost, sorry, and the latest one, that is May Ozerov, gives lower cost. So this, in short, is the security analysis that has been done by us. So on the basis of the three information set decoding algorithms, and this is the results that we have found. So I would like to acknowledge my fellow researchers, Mr. Shantan Chatterjee and Dr. Bhaskar Biswas, and this work actually is a part of the project sponsored by SAG DRDO, and I thank Mr. Harshdeep Singh, the scientist of SAG DRDO, for valuable inputs. Thank you, and I would like to have some questions if you have.
Yeah, questions? Any questions? So if there is no question, then we may move to that our next.
I had one question. See, what I wanted to know, if you look at this expression for y, it is same as in ring learning with errors. Or, even NTRU, y is AM plus E. E is errors and some message, and A is a matrix. Now, what is the relation between McAleese and RLW? Is there any relation?
Sir, will you please repeat relation between McAleese and? Hello, sir. Hello, sir.
Anand wants to
I'm
ask,
not getting.
is there a similarity between McAleese and ring learning with error because of the
Yes,
similar
yes,
equations?
yes.
So basically, the Lidacrypt, it uses the basic idea of key generation, encryption, and decryption processes of McAleese. So,
The audio is not audible.
is it better now?
Yes, yes, yes.
Yes, sir. What I was telling is that Lidacrypt actually uses the key generation, encryption, and decryption techniques, the basic techniques of McAleese. They have been modified.
No, that I know. See, what I am asking is just out of academic interest. Is there any similarity between ring learning with errors and McAleese? Because finally Y is made up of some errors and message and some matrix. This matrix in the case of McAleese is different. So I am just curious to know whether anything relationship can be built or something like that.
Okay, sir. Actually, we have not pondered upon this whether the
Okay, okay,
relationship has
okay.
exists.
Thank
So
you.
I'll obviously think about it. Yes.
Okay.